Okay, so we got the formula for the internal angles. Let's look at from another point of view at the external angles at the triangle. So you can easily say that beta, the triangle could just as well be defined by these external angles, which are basically just the complements. Beta prime, gamma, gamma prime, alpha, alpha prime. Alpha plus beta plus gamma equals pi plus SABC over r squared. We covered that. And but there's more. We can look at it in terms of the external angles just by writing this equation, replacing alpha with pi minus alpha prime being pi minus alpha, so that's pretty symmetrical. And we just get the sum of the external angles is alpha prime plus beta prime plus gamma prime equals 2 pi minus the area SABC over r squared. Now, if you look at a more complicated than a triangle polygon, you see, like, as you add more vertices, generally speaking, the internal angles keep getting larger and larger and larger, but the external angles tend to get smaller and smaller and smaller. So that really leads to a situation where the sum of the internal angles, since they're getting bigger and there's more of them, increases very rapidly. But at the very least, we know the sum of the external angles has to increase rather slowly. And here we make a claim that the sum of the external angles for any polygon is actually 2 pi minus the area of the polygon divided by r squared. And so we'll just show that is true. Pretty remarkable fact. Certainly wouldn't be something true for non-spherical coordinates. But let's look at what the proof of that might be. Okay, so let's look at whether we can prove this statement here that the sum of the external angles of any polygon, not just a triangle, is equal to 2 pi minus the area of the polygon divided by r squared. And the method for doing that will be, and I just want to give credit to the proof I'm following here is by this guy, Ivan Sopranov. I think he's a professor at Cleveland State University or someplace. Anyway, you can look up spherical triangles or Euler and Sopranov. You'll come up with his publication, and I'm sort of following that publication. I just don't want to. All I'm taking credit for is the SketchUp artwork in my own befuddled explanation here. So how do you prove this for the general polynomial? General polygon. Well, first you show it's sort of a modified version of an induction proof. Show it for the case where the number of vertices equals n equals 3. That we've already done. That's the triangle. For any triangle, the sum of those angles is 2 pi minus s poly over r squared. Then assume it's true for some arbitrary n, or assume the truth for some arbitrary n implies truth for the case n plus 1. That means show basically that if it's true for 3, it'll be true for 4. If it's true for 4, it'll be true for 5 and true for 6, and so on for all the finite numbers. So for arbitrary n, assume it's true and show that you can use that assumption to prove the n plus 1 case. Okay, some of the and I'm just going to leave out the primes here because it's just easier. I wrote that in PowerPoint. It's just easier to keep it that way. Okay, some of the assume it's true that the sum for an n gamma. So here we just draw a representation. And this is pretty much Sopranov's figure. That's why I'm trying to give him credit for it. So you draw this arbitrary figure here that shows an arbitrary polygon of n vertices, and then you add one more vertex to it, the an plus 1, and you see what happens. So for the in polygon, you assume the relationship is true. Then what changes when you add the extra polygon? Well, you get a larger area, and that area is this triangular region, and the vertex of that of the added region will be a vertex at A1, a vertex at AN plus 1, and a vertex at AN. I just drew a larger version of it here. So basically, most of the external angles going around the polygon are exactly the same. So when you want to solve for this thing that you want to demonstrate, the sum of alpha prime I from I1 to n plus 1, it's basically the same as the alpha primes from 1 to n, except for at vertex AN, vertex A1, and vertex AN plus 1. So, and the difference is, here's the angle, external angle at vertex n. What you did is subtract off, I called the internal angles here gamma 1, gamma n, and gamma n plus 1. So to get the new external angle at n plus at n, you just subtract off gamma n. The same thing here, to get the new external angle at vertex 1, A1, you just subtract off gamma 1. And then you have the new external angle, alpha prime n plus 1. So that's what I'm showing here. In terms of gamma 1, gamma n, and gamma n plus 1, the sum of external angles for the n plus 1 case is just the sum for the n case minus gamma 1, minus gamma n, and minus gamma n plus 1. And then plus pi. Okay. So if we want to solve, we can get an expression for this. This is just minus what we started out here with. That's just minus pi minus gamma 1 minus gamma n plus 1. That's what we showed at the beginning. It's just minus pi minus the area of this new triangle that we added on, divided by r square. So we replace minus gamma 1, gamma n plus 1, those random angles, with this expression. So we end up getting 2 pi minus the area of the n polygon over r square minus the area of the triangle over r square, and that just equals 2 pi minus the area of the n plus 1 polygon divided by r square. So that's what we needed to prove to solve the induction criterion. So if it's true for n, it's true for n plus 1. Since it's true for 3, it's true for 4, 5, 6, 7, any n. So in general, for any spherical polygon, we can now say that the sum of the external angles is 2 pi minus the area of the polygon divided by r squared. And just as a note, we're going to use this in the next part. If it's a unit sphere, a lot of times people work with unit spheres in spherical trigonometry, just so you can drop out the r. Then the area, you can solve for the area of the polygon. The area of any polygon on a unit sphere is 2 pi minus the sum of the external angles of that polygon. So that's a pretty amazing result already.